As I mentioned in the last talk, this one that Anshu and I are going to be giving about managing computational experiments really is a continuation of what we just talked about in terms of lab notebooks. So we're just going to keep ramping up a little bit. So I'm going to be talking for the first 30 minutes about something that I would call computational laboratory notebooks, what they are conceptually, how I try to use them, for instance. I'm bouncing that off of my experience as an experimentalist again. So this is sort of a recapitulation of what I talked about in the last one, my high-level experiences. I'll add just in a few other things to try to motivate some of the difficulties that we have. So for instance, when you work in a physical laboratory next to an instrument in a single building, it's really quite nice because your collaborators are right next to you, which means that they're ready to talk, they're ready to share, we're ready to learn from each other. What that means in terms of knowledge management is that creating knowledge, generating knowledge is natural. It just happens. And generally, the communication of that is implicit. And if someone was, if we generate some knowledge and someone wasn't there, we can very easily get them up to date. So in an experimental laboratory, for instance, I really didn't need to generate much documentation beyond lab notes and articles. That was it. That environment was so easy. In our digital environment, in the computational sciences world, unfortunately, I don't think it's that easy. Another thing I want to do to try to add some context to some of the questions I might raise is that in my personal experience when I was a graduate student in physics, I do believe that I went through something that was akin to an apprenticeship. And I want to differentiate between a mentorship. So yes, the people that I was working with, they were trying to guide me. I think they were trying to help me make good decisions. But the reality was they obviously had a lot more skill and knowledge and understanding than I did. And I think they really tried to build me up into a researcher. Right? And they tried, as part of that, they tried to get me to understand the need and how to do that low-level science that we need to do. Final thing is because of my wacky experience of jumping from one world to the next, I do generally tend to have this idea of trying to, rather than seek out differences, try to seek out the commonalities. And when I do find those commonalities, try to adapt them to the new world that I'm in. That's a little bit related to what we heard David talk about this morning as well. So when we talked about the DIKUW, we didn't actually talk about the W, which was the wisdom. There wasn't really any need to in terms of that previous talk. But in the interest of trying to adapt what I've learned from my previous work experiences to my current one, and trying to ramp up to this notion of the computational laboratory environments, I did find it useful to try to think about what wisdom might mean to me. And in this particular case, I'm talking about the accumulated wisdom of a community. So in this case, the experimental world, the observational environment I was in, and in the computational sciences world. So oftentimes in life and in labs, we learn and repeat short phrases. So in the general sense, we have phrases like the devil's in the details. If it's worth doing well. A counterpoint to that is perfect is the enemy of good, and something that I used to hear in experimental laboratories, I'd rather be correct than fast, right? So we have some from the hardware, working on hardware. We'll go over those in details. I try to adapt those to the world of software, but I did try to sit down and think of similar types of statements for the software world. I had a harder time doing that. Not because there is no accumulated wisdom in the software world. I certainly don't believe that, but I do believe that to some degree the software world is potentially just very large and diverse. So when you do find some wisdom or some sub-community finds wisdom, it might not translate to other worlds. I sort of believe that that's probably behind this, or maybe I just haven't come across enough of these yet. So I did my best. The first one I came up with, premature optimization is the root of all evil, which is a fairly well-known statement from Donald Knuth. One that a coworker at the observatory told me is code is meant to be written once and read many times. That's very clearly an oversimplification, but I think we get the gist. The idea is not to write programs for ourselves, but the people who are going to come after us, right? And then the other one is less a statement and more of an idea of code smells. So for people who aren't aware of code smells, this happens when you're reading or writing code, and you start to get this sinking feeling that this is really not how the code should be written, or it should go better than this. Essentially, the idea is then what you're smelling is that the code is rotting in front of you. And so then the wisdom is you should go ahead and refactor that code, or perhaps you need to reassess your design because the design is what's forcing you to write bad code or has forced other people to write bad code. So in terms of hardware now, there's a couple, the two ones that we're going to look at first are know your tools and the right tool for the job. The general idea of this is that just because a tool is sitting in front of me and I have some vague idea of how to use it doesn't mean that I should use it. I should figure out how to use it. I should read the manual so that I don't damage the tool and I don't damage the work piece that I'm working on. So how can we translate that, know your tools and use the right tool for the jobs to the computational world? So the first time I came across this was many years ago with a productivity language like Python and its packages. Oftentimes you'll come across these amazing functions that are very easy to use, hence productive. They have 1 or 2 mandatory arguments that you give them, but they have a list of something like 10 or 20 different optional arguments, where each optional argument is given a default value. So in the spirit of know your tools, I don't just simply use those right away. I'm going to actually investigate which each one of those 10 different optional arguments are, make a decision about what the value should be, and in the name of explicit and defensive programming, I'll actually write an argument for each one of these even though they're optional. So a flip side to this is if I'm designing a library, I have all of this knowledge about what I've designed. I should communicate to the people who are going to use my library so that they can actually learn how to use my tool effectively. So it's similar to this idea of functions. I have certainly come across some of those functions where I've wanted to learn what all of those different optional values are, but I simply have not been able to find out what they are. Therefore, I will choose not to use that tool. Another question, and this is related a little bit to the idea of an apprenticeship, is it okay to use high-level productivity tools blindly? So as an example of this, when I came into the computational sciences world, I didn't necessarily know that much about setting up software stacks. And we've seen from Todd's talk how very difficult that could be. And if I had come across some container that already had this nice software environment that I wanted to use, is that acceptable for me to just blindly use that? Or in the spirit of an apprenticeship, should I have forced myself to learn enough about that world, about the low-level difficulties, the pitfalls, and the challenges of setting up that before I actually use that container? In other words, maybe I shouldn't use a container unless I know that I would actually be capable of setting up that container myself. So that's a case, I think, of know your tools as well. So here's an example that I went through in terms of know your tools. This is the idea of I want to explicitly construct my software stacks, my environments. Obviously I want to get that right, and I don't want to be right by accident or by coincidence. So, from working with people, I became aware of this tool called LDD, which will tell you what are the external dependencies of the object that you pass to that program. And this is something that I will do. It's just a simple sanity check to make sure that things are where I think they are. So here what I've done is I've gone to Bebop, and I've run an actual LDD on an actual binary that I use. And I've done it in 2 different software environments. One I would call the build environment. One would be the execution environment, and the only difference is for the build, I decided to load Anaconda because we're imagining that just basic Python was necessary as part of the building process. And what we see here is the LDD output. So on the left is the dependencies for that binary. On the right are how those dependencies would be satisfied in that current software environment. So what I see, for instance, is that I need MKL libraries, 3 of them. And when I have Anaconda loaded, it is actually going to satisfy those by pulling in libraries that came in with Anaconda when I loaded that module. That's not what I wanted. That's not what I thought I was going to get. What I did expect to get was on the execution side, where I see I'm going to be getting those 3 MKL libraries, for instance, from the actual module that I loaded. Right? So this is just a simple sanity check I do. I brought this example up as well because I started to realize that these are types of notes that I should actually be recording. Right? I want to write into my build logs and my job logs what the software environment was and do this nice little LDD sanity check. So I can build my build and job scripts to capture that sort of data for me in an automated way. So measure twice and cut once. I'm sure people have heard this phrase before. It's a good one. The idea here is that some of actions that we take are not reversible. We need to slow down. We need to think so that we don't waste resources. The idea is essentially to do an appropriate level of planning. So rather than relate this to the computational world, I relate this to the observatory world. When I first started using the telescopes at night to gather technical data for the systems that I was studying, people from the science staff would have eventually come up and let me know that it cost something like 50,000 euros per hour to operate one of the telescopes, which was their not so subtle way of letting me know that I need to get my act together. I can't just show up at the telescope with some vague idea of what I want to do. I need to be able to come with an appropriate level of planning so I can make use of that telescope and get maximum impact of those resources in my effort. So I can say, these phrases are lovely because what in the world does appropriate mean? After using the telescope 2 or 3 times, I really did start to come up with an idea of what appropriate was. Of course, at the beginning, I had no idea. In the computational world, obviously, I think that example translates over almost immediately. I did speak with Bronson Messer, who is the director of science at the OLCF, and he told me that it costs approximately $90,000 to use Summit for 1 hour, so more or less the same ballpark as the telescope. So this isn't much a statement, but just sort of an attitude is clean your workspace. So in an experimental laboratory, I think if it's a good laboratory, they spend the last 15 or 30 minutes of every day just stopping what they were doing, cleaning things up. I'm going to clean my tools, I'm going to put them back, I'm going to put things into a safe space. I want to have everything clean and ready for the next day. I think that's important because fundamentally what you're doing is respecting your tools, you're respecting your coworkers, and you're respecting this laboratory environment and you're working in, because you know that if you do have this respect, you'll probably get a better job and you'll probably be happier doing that job. Right? So what does that mean in terms of the computational world? I take it to mean write good commit messages. I may maintain my issues, PRs, and documentations up to date in the moment. It's very nice and comforting to say, well, I'll just write that document 3 months down the line, but that's either never going to happen or I'm not going to do a very good job because I've forgotten everything. If I've been working on a project for 2 weeks and I'm about to transition to another one, I'll stop the last half day, I'll update my documents, I'll go and I'll look, see if I need to organize my files. If I have some clone that's left in an intermediate state, then I'll either get it into a clean state or I'll document why it's an intermediate state and what are the next steps that I need to take when I come back to that project. So those are the ideas of the wisdom, right? Hopefully some of those are going to factor into what I'm talking about in terms of setting up a computational laboratory environment. But first I'm going to tell you what I like about experimental laboratory environments. The idea is that at some point I'm sitting in the lab because I want to execute some science. And what I want to do is have all of my tools at hand. I want to have them clean and ready for use. I want to know how I'm going to use them and how I expect to use them for that particular case. I want to make sure that my instrument is well characterized and configured so I know that it's going to be generating data, high quality data at the level that I need for my study. If there's something wrong with it, if it's underperforming, I need to obviously know that that's happening and then understanding how that's affecting the data so that I make sure that I know how to use that data appropriately. And then finally, I want to be able to take comprehensive lab notes quickly and easily, so that's not putting in too much of a barrier. Right? That's what I want. Fundamentally, the idea is I want to do an appropriate level of planning, make sure everything's ready and clean, so that when I just want to execute that study, that's all I have to think about. I want to concentrate on just that, concentrate on acquiring the data, analyzing the data, drawing conclusions, designing my next steps, and recording the work for that reproducibility. Okay? So what do we want then in computational laboratory environments? I think we want that same idea, right? We want to achieve that same goal. One of the benefits that we have here is we're not sitting in some giant expensive lab space next to some giant expensive instrument. We have the flexibility to create as many little virtual computational environments as we want. Right? We can choose to make them as simple and minimal as we want, with the idea then that we can tailor the level of formality, complexity, the level of tooling and automation that we need to the particular task that's associated with that laboratory environment that we're building up. One of our fundamental priorities is I want to be storing the context and metadata next to the data that it's associated with. And that was something that we actually saw in David's morning talk. That was one of their bullet points, right, about things that you should try to achieve. So nothing new there. So what does it mean to have different environments? Well, we can have different types, first and foremost. So one would be a test environment. So for each code repository, we might want to build up a test environment. In that code repository, we'll have the computational code. We'll also have the test code. But everything about how we run that test can be offloaded into this test environment. So that can be how we're going to set up the software environments, how we're going to log information about changes to those, how we're going to set up the test suites, how we're going to run them, how we're going to determine pass-fail, and how we're going to determine communicate pass-fail to the developers. Okay? In the name of minimal and simple, we can have one environment per scientific study, and developers can choose to come up with their own dedicated development environment if they find that to be useful. Okay, so what do we want really out of all these environments? We want them to be encapsulated. Encapsulation, I think, is just a general design principle, something that we like. Encapsulation modularity, no difference here. What that can mean is dedicated documentation, dedicated software environments. And principally what we want is to be able to update and manage those lab environments independently. So what would happen, for instance, if I start to violate this encapsulation? So if there's a platform with a nice test environment there with all the software environments set up, and I want to go and execute a study on that same platform, in the name of productivity, I could just go there and piggyback and violate that encapsulation and use their environments. Let's imagine I go and I acquire half of the data that I need for my study using those software environments, but then unbeknownst to me, that team that's managing the test environment has to update their software environments. If they don't know that I'm piggybacking off of them or they forget to tell me, then I'm going to acquire the rest of my data with a different scientific software environment, which might be very damaging to what I'm doing. Right? Okay, so how can we actually take the notion of a computational laboratory environment into reality? Well, the idea is we want simple and minimal environments. Let's put each simple and minimal environment into a simple and minimal repository. Clean, right? So instead of having something like we have one massive repository where we're stuffing all the code, stuffing everything to do with tests and studies into this, we can try to blow that apart into a system of repositories where hopefully each repository is fairly simple and we can manage the complexity at the level of a system of repository in a nice way. So systems of repository is something that I see more and more people using for different reasons. It seems like everyone's coming to this conclusion that this is really going to be the best organizing way for attacking different challenges. I don't think there's anything new about this. So if you were on a large team or working on a sort of a team of teams, a distributed sense, I'm sure you've been using systems of repositories for a very long time, for example. So here what I've put is an example of what a system of repositories might look like for FlashX. So we have FlashX sitting in its code repository. It needs functionality from Paramesh and AMRX, each of which is going to be in its own repository. Together, this subsystem forms a code repo. And then we have these satellites of laboratory environments that have a use relationship to it. So we have a test environment. Some developers decided to put in their development environments. And then we have a couple different study repos in terms of scaling performance and core collapse, let's say. To give you some idea, though, it doesn't just have to be that simple use. These different study repos might actually have a relies-on relationship to this test environment in terms of doing their testing and their verification. OK. So how would we go about constructing a computational lab environment? So this is clearly something that is going to be different for each study, for each different people. Again, we want to tailor this to the team and to the work that they're going to be doing. I generally start from the bottom. And in the spirit of some things that we heard in this morning, where I'm starting and where I would like to be with this is a fairly far distance. So at no point have I tried to just jump to the final solution. That's just not going to work. I have to go from one environment to the next, adding on a next little step. So I identify what are the pain points from the previous one, and I try to add that on. And personally, I've not given priority to things like automation or trying to use the latest and greatest tools. My priority is always on trying to do rigorous and reproducible science. So I sacrifice some of the other things, and hopefully someday I'll get there as I take all of my little baby steps. So I do start from the bottom in accord with that my priorities. What this means fundamentally is I'm going to be generating data files, and I want to make sure that I always keep those available for the foreseeable future. So that's my first starting point. I want to come up with some scheme for how I'm going to store those files, how I'm going to protect them so they're not lost or overwritten accidentally. And I also want to make sure that they're maintained. And I also want to make sure that people can access them so that they're shared easily so that people can do their science, their analysis on that data easily. And so once I have that scheme sort of set up, then I can start focusing on the software environments. So maybe I need to set up an environment in terms of managing my tools. I can use Todd's SPAC environment to manage all the complexities of the compilers, interpreters, and libraries. And I could potentially use Python virtual environments for the data analysis tool. And so once that's in place, now I can start talking about building and jobs. So that's why I can start putting in levels of my platform-specific build scripts, my platform-specific job scripts, and then we can start thinking about testing, verification, and validation analysis. And of course, we want to have some notion of how we're going to keep lab notes. So we need to have some scheme of how we're going to participate in acquiring those lab notes within this environment that we're setting up. So hopefully when you look at this, you're getting some idea that this is us sitting in a virtual lab. I've got all my tools clean and ready, and I'm ready to start really focusing on just executing the science. And I've got my documentation infrastructure set up so that I can take lab notes without them getting too much in the way. Okay? So I do want to mention at this point, again, the idea here is to do an appropriate level of planning, right? And also the idea here is to get things to be clean. So if you are working in an environment where you don't think people are going to be working in that spirit of keeping your workspace clean, maybe what you can do is in these very critical layers, actually put in gatekeepers, for instance, who are going to make sure that that cleanliness happens because that will be very important, right? And again, and sort of thinking back to what Carlos said, what I want to try to do is avoid that situation where when I start operating in this environment, I get that sinking feeling that something's going wrong, that my process and tools are not good. And the way Carlo explained this was that sometimes he would get this feeling that what he was doing was in-flight airplane repair, right? That's kind of what we want to avoid. But again, in the name of appropriate level of preparation, we don't want to go overkill. and try to build the most amazing, perfect environment to try to avoid that at all costs, that's probably not worth our effort. I think we have to accept that sometimes that's going to happen, and hopefully if we've done an appropriate level of planning, it won't happen so often and it won't be so catastrophic when it does. Okay, so the last couple slides I'm going to concentrate on documentation. So we don't want a single 10,000 line README. I think this is what we were talking about at the end of the last slide. I think in the computational sciences world, we can't have just one or two streams of lab notes. I think there are really a great many different streams of lab notes. And my experience has been if I try to force all of those into one single tool like Microsoft OneNote, that just doesn't work. What we probably need to do is understand the realities of each of those streams of lab notes and choose the right tool for the job, right? The right tool for each one of those streams. So in some case, that might be a git commit message, right? In some cases, it might be an issue. And that leads us to having really a sort of a collection of tools that we need to use. So what are the different streams of lab notes that we might have? Well, we can have document the changes in the code repo, the construction and the changes to the software environments, changes to our analysis tools, changes to our build and job scripts, and then the notebook where we're going to be detailing the experiments, how we designed and executed them. So READMEs do have a place, I think. They're quite useful. I usually use Markdown because that's just so simple and nice. The way I use the READMEs is sometimes for documenting changes to the software environment. That seems effective. They also seem very effective as high-level roadmaps. These are the documents where I put in things like my motivations, my assumptions, my design decisions, my conclusions and results. They should be concise and they should be living documents, right? As I go through and I make my changes, I want to update them, right? If you're doing a study where you're doing an exploration, so maybe I do a phase 1 study first, and based on the results of that, I determine what I should do in terms of a phase 2. Maybe what you can do is put a README for each one of those phases to document that particular phase at a high enough level. The idea would be that if someone were to come into this repo, this environment, and want to get a quick idea of what's being done, hopefully just reading through those READMEs would be a good step. So we also talked about this a little bit. How can we use version control tools to do lab notes? The idea was a commit message. That's something that I have to do. And in some case, that seems, for some streams of lab notes, that might be the good thing to do. In some sense, that really is the closest analog to having the paper notebook next to the instrument, right? I'm putting my commit messages right next to the instrument. If we're doing design and things like that, we can use issues and pull requests, for instance, in an appropriate way. Data, context, and metadata, we went over this a little bit. We can try to put in as much automation as possible, so we can have build scripts and job scripts that are going to document as much of my lab notes as possible. We can also do what I think a lot of people do, which is document a lot of the metadata, such as build names, usernames, git hashes, and the headers of the files themselves, so that the files are self-documenting. And then finally, one thing that I've been using a lot for these is Jupyter Notebooks. This allows me to put so the context and the metadata as close to the data as possible. It allows me to also put in my analysis, conclusions and results right in one place. They really are quite powerful. So at the top, what I might do is have a high-level design with motivation, conclusion, results, so a living portion of that document. Below that, I can put where I've executed the experiment in terms of recipes. This is what I did as sort of bullet points. So that's frozen at creation. Then I load the data and I can start generating visualizations, and I can comment on those in Markdown in the results. So these are really, I find them to be really quite powerful. They can be quite concise. They really put everything into them. They're interesting to me because they don't fit onto that documentation hierarchy. They really are little bits and pieces are from different places on that documentation hierarchy, and I wonder if why they're so effective for me. So is this working? I will say that this is a work in progress. I've been sort of working towards this for 5 years. I first came in, like I said, I wanted lab notebooks, and I didn't find them. There were other things that I didn't find. And so it's gotten to the point where I can say that when I stand up one study based on the other ones, it's taking me less and less time. I'm not having to do as much adaptation. I can also say that what I'd use for one project works quite well for another project. So it seems to be that I'm converging on something that works for me in a more general sense. I'm also not the only one who is doing these types of things. So there's a BSSW fellow named Ivo Jimenez from 2018 who worked on a tool called Popper, where he talked about implementing scientific exploration pipelines to yield reproducible results. And then I'm aware of a PhD student at George Washington named Aaron Lentner who's built up a Flash kit, which is a high-level interface for helping users structure and manage research with FlashX. And what these are essentially creating a new level of tooling and processes that allow you to focus plainly on just executing your study, which is essentially what I would say the computational laboratory environment is. So hopefully now this is a little bit more concrete. I've built up an example laboratory environment in a GitHub repo. You can go ahead and follow that link if you're interested in looking at it. And with that, I think I will hand over to Anshu.
In the meantime, if you have questions for you.
If anyone has any questions, we can take them now or we can take them to the end. I will say if you have any questions about what I've talked about in lab notebooks in the computational lab environments, if you want to work over this in detail, the example I've put up, just come and ask me. At the end, I'm happy to talk. If you want to come and argue with me, I'm always up for a good argument as well.
So I'm switching gears a little bit, though this is still about how to conduct your computational experiments. And this is that so far we've talked about setting up the infrastructure on how to collect and analyze your results, but we still haven't talked about what you need to do in terms of preparing your code and preparing yourself for running these experiments and the steps that you need to do in order to do so. So this is basically, this section is talking about how do you plan for a successful simulation campaign. And even though this is talking about simulation, that is probably as applicable to other forms of doing computational experiments. But I'm speaking to simulation because that's what I'm most familiar with. Oh. So we came to this conclusion a while ago, back in 2004-2005 timeframe, that actually running the simulation is more like a craft. That for scientific discovery, you develop a nose for when you are going to be successful and when you are not going to be successful, and that it relies more upon experience and acquired wisdom than any scientific set of steps that you can follow one after another. So it really is something in which people need to be trained and people need to learn from others. So it's more like an apprenticeship that Jared talked about, that you need to sort of have in order to become a successful computational scientist. And so the first step that I learned in close association in working with one particularly conscientious and careful scientist, and most of the lessons that I'm distilling here in this talk are basically learning with this one person whose work was very, very admirable and became less painful compared to any of the previous simulation campaigns that I had been part of. This was a pleasurable experience by comparison. So he insisted on doing planning ahead of time, and the reasons that he knew and the reasons that continue to be valid now also is that these machines are very expensive and rare resources. As Jared said, some it takes $90,000 per hour. So operating them is also very expensive, and you know, you're not the only one who wants to use those. So there's a competition going for these resources, and so you're likely to be charting new scientific territory with these experiments. So in these experiments that you're running, if you made a mistake and got garbage results for a large scale run, you've just literally wasted hundreds of thousands of dollars. Not only you wasted hundreds of thousands of dollars, this is a lost opportunity not just for you, but for someone else also who could have utilized the same resources better than you if they had done, if the work was done with more planning, right? The part where you are likely charting new scientific territory brings up this issue that you may have been running and testing your code, but now you are exercising it in ways that you probably have not exercised it in the past. So you don't know all aspects of its behavior. Some solvers in your code may run up against the limit of their validity. Sometimes in-flight correction may be needed for parameters to continue with the study. So this is different from the type of in-flight correction that Jared was talking about. Jared was talking about correction that you may need to do because you haven't planned well enough. I'm saying that you cannot completely eliminate the possibility of still having to do in-flight repair because you are just going into a new regime, a new territory, doing something that hasn't been done before. So what is coming out is something that causes you to make changes to your execution plan. So in your planning, what your objective should be is that you should aim for no surprises, but you should be prepared for them because they happen. So I will say that the flash center failure that David talked about this morning, where we did not have the particles code working right, and it took us a very long time to start actually looking at our results. At that time, there were 5 ASC Alliance centers that were funded by NNSA, and each one of those centers was given the same opportunity. And because we had this one very careful, dedicated scientist, we were the only group that succeeded in getting scientific results out of that opportunity. The remaining 4 just did not. So the question is, how do you plan? The very first step in planning is to do a very targeted verification on the target platform. Because the daily testing may not be enough, because you are now operating on a platform on which you may not be running your regular testing. So you need to do dedicated testing on that platform. You have to explore the validity regime of the solvers that you are going to be using in the context in which you are going to be using them for the study that you are planning. In order to do that, you typically do what are called pathfinder runs, which are trying to mimic the behavior of the code that of the way in which your code is going to be exercised during the actual study. And so what these pathfinder runs do, you may want to run a bunch of 2D runs in similar circumstances, followed by simpler 3D runs that give you extrapolation possibilities, etc. What they do, these pathfinder runs, is give you a possibility of the cost benefit analysis that you might want to do, so that you can do this trade-off between fidelity and the ability to reach the end of the target simulation that you are trying to do, so that you can reach your science goal in allocated goals in your allocated resources. It is important to develop helpful diagnostics, the quick checking ones, so that on an ongoing basis you are checking the health of your run. For example, if you are doing a simulation of anything that is using hydrodynamics and your density goes negative, that is a clear red flag that your simulation is going in the wrong direction, and that is a very cheap check to make. So those kinds of diagnostics are very important to develop ahead of time, which you should be checking for like almost per time step. Then also you should have some hierarchy of analysis, so that, because full analysis takes a long time, but you should have hierarchy of analysis that lets you know again whether your simulation is going in the right direction or the wrong direction. This may be, you may want to take a slice of a 2D slice of the code and do its visualization, do some 1D plotting, etc., to make sure that there is nothing unphysical going on, that structures are not showing up where you don't expect them, etc. So those should be developed. And so I'm going to illustrate these with a story of one simulation campaign that I was a very close part of. Again, this was led by the same scientist, and like I said, I learned all of these almost at his feet. So the story is that we were going to do simulations of type 1a supernovae, and this was in the time frame of 2006-2007. Until then, all of the simulations of type 1a supernovae had been done either in 2D or in a symmetric mode, where you just simulated an octant and assumed that because a star is symmetric, that everything is going to come out, that it is representative case for what you wanted to do. For type 1a supernovae, there was this one specific problem, is that its spectrum, so it has a very fixed light curve, which is powered by decay of nickel 56, but then there are traces of intermediate elements, which speaks of a deflagration to a detonation transition. Now, in a star, it is impossible to imagine how a deflagration to detonation transition will happen, because a star can continue to expand. What would cause the pressure conditions that would cause it to explode? A very tantalizing indication had come from a 2D run that if you violated the symmetry of the simulation and that if you started an ignition slightly off center, that this could lead to a detonation where the deflagration would run for about 1 to 2 seconds, and then there would be a detonation which would be absolutely consistent with the traces of elements that were seen in the spectrum. So, this is what we needed to do, and at that time this was going to be a full 3D run which was not an octant, it was going to be a full star, and it was absolutely the first of its kind. So, we started to do pathfinder runs. But before that, first thing that we needed to do was develop a test that would represent this problem so that we could exercise it on the target platform. The challenge with that was that features that we need to do take a long time to develop. So, we would need to run for hours before features would develop enough to tell us whether the code would run fine on the target platform. One option for that would be, of course, to do a dump and do a restart, but the I/O was very slow, so that also was not an option. So, the first thing we did was we developed a manufactured way of creating these structures that we wanted to do, and that was not a non-trivial exercise, but ultimately we developed a sample run which had the same characteristics that the actual simulation was going to have, but it was not physical truly, it just developed the structures we needed to do. And actually understanding of the physical people use their physics understanding to create conditions that would develop comparable complexity in a different way. So, that was the first step. The second step was that we used this new test to characterize the performance behavior on the target platform, because we wanted to know if the standard performance studies could not give crucial information, because we were exercising code in a different way and we were combining many more pieces of physics than we had done in the past. And also the AMR pattern, when you are working with AMR, ends up being completely different for each instance of the application that you are running with AMR. So, it is very hard to predict what from other performance studies what the AMR pattern was going to be. And then we needed to examine the trade-offs possible and the interoperability behavior in a much more closely resembling the real simulation situation. So, what we did was we did a bunch of full fidelity 2D runs and a set of 3D runs using the new test that provided us with enough information to extrapolate and estimate the needed CPU hours. The thing that happened was we found out that we were about an order of magnitude off in terms of resources that we were going to have to complete this run. So, now we needed to look for optimization opportunities, and this is where if we had gone into this simulation without this preparation and just started, we would have gotten about 2/3 of the way, about 2/3 of the way into the evolution, and then we would simply run out of resources, because as the simulation is running, the structure grows and grows, and per time step amount of resources need also continue to go. So, last 1/3 run was going to need so many more resources that we were just not going to be able to complete the run at all. So, now we have to, so we started looking for opportunities here and really started to do trade-off between fidelity and the amount of time that we needed, and basically crystallize the goals that we wanted to realize from this study. So, I am not going to go into the details of each of the trade-offs we made. They are listed in the reference that is listed here, but the important thing that I want to say is that the traditional approach that people take to optimization of trying to squeeze more floating point operations from the target platform was just not going to work for us. And in fact, what we did was we looked at physics intuitions, we looked at algorithm possibilities, and all of the optimizations that we made then became useful for the later studies also. So, in that sense also this was a very useful exercise. It was a combination of identifying where redundant refinements were happening and getting rid of them, coarsening some of the physics computation if they were not going to have too much impact on the overall outcome, and also moving some computations to post processing instead of doing them in line. With all of that, And then final step was preparing for diagnostics and quick analysis mechanisms. So the first one was, of course, the conservation of mass, momentum, and energy. And then with each of the runs, we were generating log files. So the changes in the time step would give an indication if the code was going off in a wrong direction, and spikes in variable values, etc. So we were doing quick visualization of random 2D stencils and 1D quantities. To relate this back to the way in which what Jared talks about in the sense of lab notebook artifacts, what every run was registering the configurations and runtime parameters in a log file. So they were recorded. The log files were cumulative, which means that if we restarted the code from one point, the log file was just added on to the same run, and it was collecting all of the data. We had, before starting the run, we had dedicated space and a directory structure for collecting the data, and there were gatekeepers assigned so that the data wouldn't be accidentally removed. And then we had developed scripts to move data from the scratch where the run was being done to this dedicated space. So that planning had gone into, that was our all computational lab environment. Remember that this is more than 15 years ago. So this was pretty sophisticated for its time, but this is what basically we had. And so the outcome of all of this planning was, of course, a successful complaint, but that was not without hitches. But and one of the hitch we found out soon enough, in that we did not give the same level of care to the runs that we were doing for optimization. So we were not saving up all of the data because that data was considered disposable. And so all that we did was we documented the code changes and did not save the data. So then when we wrote this paper, the paper that was the reference, the referee asked for details from optimizations, and we did not have them. We did not have the data that the referee was asking for. Fortunately, we were able to satisfy the referee with reasoning and other supporting evidence that we produced for them, but this could have gone badly. And just because we did not foresee the need to preserve that data and got rid of it too quickly. Actually, we didn't get rid of it, we just didn't keep track of where the data was. So the summary and takeaways from all of these combined talks is that good science with computation is a craft. People need training in them, in how to do it. You can't just come into the field and just do it and get good outcome. It's just not going to happen. The machines are expensive to build and run, and so while they provide great opportunity to work, they also give you a great deal of responsibility to make sure that you are doing everything possible that you need to do to meet expectations. And reproducible results in science are a necessity, not a luxury. So you have to work with the assumption that you are going to do sensible, reproducible, believable, credible science. And here is a quote that I find quite illustrative, is that a parameter combination that induces erroneous results is easily selected. And if you don't plan well, it's very much possible that that can happen. That's it. Thank you.